This video is on the least squares problem. In this section, we generalize the method that we use to find the least squares regression line of a set of points in the plane to arbitrary m by n matrices. By generalizing this method, we'll be able to do regression for any polynomial with any number of variables in any degree. The reason is because if you view the polynomial in terms of the coefficients, then what we have is something that's linear in the coefficients. And so this sets up a system of linear equations which we can apply linear algebra to. So the basic idea is that you have a set of points that doesn't exactly fit your model. So this leads to a system of linear equations that's inconsistent. Okay, so the system of linear equations doesn't have an exact solution. So what we try to do is to find the best fit model in the least square sense. Right, so by least squares we mean that we're for the system ax equals b, we try to minimize the squared length of ax minus b. Okay, so because we're looking at systems where ax equals b doesn't have an exact solution, we can solve the least squares problem by following this procedure. Right, so you start with your system ax equals b, then you multiply both sides on the left by A transpose, so you get a new system of linear equations. Right, so because A is m by n and A transpose is n by m, this new system of linear equations is now an n by n system. And so the name of this system is called the normal equations to the least squares problem. And the solution x of the normal equations will give the solution to the least squares problem. Okay, so so this procedure is fairly straightforward, right? So starting with any system x equals b, you set up this new system by just multiplying both sides on the left by A transpose, and then this new system we just solve for x. So one thing to note is that we multiply on the left by A transpose because x equals b is inconsistent, but even in the situation where x equals b has a solution, this will give you the normal equation will give you the same solution. Okay, so we're gonna apply the procedure discussed in the previous page to finding the least squares regression line for this given set of points. Okay, so because we want to find a regression line, our model should be the general equation for a line, right? So a0 plus a1 times x, and so we can now set up our system of linear equations by plugging all the x and y coordinates into this model. Right, so we plug in the points, each one by one. So starting with the first one, so x is 0, y is 0. So plugging in x, you get a0 plus 0 times a1 equals y, which is 0. And then the second point, 2 comma 2, a0 plus a1 times 2 equals y, which is also 2. And the next point, 3 comma 6, we get a0 plus 3a1 equals 6. And then finally 4 comma 12, a0 plus a1 times x, which is 4, so you got 4a1 equals y, which is 12. Okay, so this is our system of linear equations. And in matrix form, right, so the coefficient matrix, so we're thinking of the a0, the coefficients a0 and a1 as the unknowns, right? So the coefficient matrix is 1 0, 1 2, 1 3, 1 4 times a0 a1 equals the constant vector, which is 0 2 6 12. Right, so this is the matrix form of the equation. So if you notice, right, so we have all ones on this column. What are these? These are just the x coordinates, right? So 0 2 3 4, these are the x coordinates. And then this column vector is just all the y coordinates, 0 2 6 12. Okay, so this is our equation, ax equals b. Okay, so now we set up our normal equations. So multiplying on the left by A transpose. Right, so taking A transpose, columns become rows, right? So now it's 1 1 1 1 0 2 3 4. This is A, then x is a0 a1 equals A transpose again. Times b, which is this. Okay, so now let's carry through the multiplication, right? So first, this multiplication. So it's a 2 by 4 times a 4 by 2, so it becomes a 2 by 2. One plus 1 plus 1 plus 1 is 4. Notice how this is just the number of points that we have. And this is 0 plus 2 plus 3 plus 4, which is 9. It's just the sum of the x's. And this dot this is again 0 plus 2 plus 3 plus 4 is 9. So again, that's the sum of the x's. And this is 0 plus 2 times 2 plus 3 squared plus 4 squared is, what is that, 4 plus 9 is 13 plus 16 is 29. So that's just the sum of the x's squared. Times a0 a1, and then now multiplying this, 0 plus 2 plus 6 plus 12. So that's 8 plus 12 is 20. Right, so notice that it's just the sum of the y's. And this is 2 squared, 2 times 2 plus 3 times 6 plus 4 times 12. So that's 4 plus 18 is 22. 22 plus 48 is 70. So that's these are the x's, these are y's. So the dot product is just the sum of the x times y's. Okay, so now we have this 2 by 2 system. And So if I want to solve for A0, A1, I can just take A inverse, right? I take the inverse of this. Right, so it's 1 over the determinant. Okay, so what am I doing? So I'm multiplying on the left by the inverse, right? So it's 4, 9, 9, 29. Taking the inverse of this matrix, and then multiplying by this vector. Okay, so this is just the 2 by 2 inverse, right? So 1 over the determinant. So AD is 4 times 29 minus BC, which is 9 times 9. And then these two switches places, so 29, 4, and then these become negative, so negative 9 times the vector 2070. Okay, so what is this? This is 4 times 29 is 116. This is a 9. Right, so 116 minus 81 is 35. And what is this matrix product? So 29 times 20 minus 9 times 70 is negative 50. And what is this? Negative 9 times 20 plus 4 times 70 is 100. Okay, so negative 50 over 35 reduces dividing by 5, so you get negative 10 over 7. And then 100 over 35, again dividing by 10, you get 10 over 7. No, 20 over 7. Okay. So, what do we have? Right, so A0 is equal to negative 10 over 7, and A1 is equal to 20 over 7. So we get that our regression line y hat is equal to negative 10 over 7 plus 20 over 7x. Okay, so we can check to see how good of a fit this is, right? So so if I go into stat and edit, I can enter in the 4 points, right? So the x values go in the first column, y values go into the second column. So 0, 2, 3, 4, 0, 2, 6, 12 are the y values. And then now I can do stat plot for these points, right? So stat plot, I can turn stat plot on, right? So the x values were in L1, y values were in L2. So now I can plot the scatter plot. So to fit all points in, I will do zoom stat. And now I will graph my regression line, which was negative 10 over 7 plus 20 over 7 x. Okay, so we see that this is the regression line compared to the scatter plot. Okay, so this is what the linear model looks like. Okay, so so that's how we can calculate the regression line. Right, so basically, by plugging the coordinates of the points into the model, we can set up this system of linear equations, and then we can do this calculation for the normal equations to obtain the unknown coefficients for our model. Okay, so in the second part here, what we're going to do is we're going to take the same 4 points from before, but instead of using a linear model, I'm going to look for a quadratic model. Right, so I want to try to fit this data with a quadratic equation. So now our model will go up to x squared. Right, so the general form would be y equals a0 plus a1x plus a2x squared. Right, so now I have 3 coefficients. And okay, so to streamline this process, right? So how is this matrix A constructed, right? So as you plug in the points, right? So the coordinate of the coefficient of A0 is 1, the coefficient of A1 is x, and the coefficient of A2 is x squared, right? So we'll have a 4x3 matrix because there's 4 points, and the way we enter the first column is going to be all 1s because the coefficient of A0 is 1. The second column, so is coefficient of A1, which are the x values, and then the coefficient of A2 are the x squared values. Right, and our model has 3 unknowns, A0, A1, A2, and then the vector B is all the y values. Okay, so I can just set up the matrix equation straight away, right? So this is all 1s, 1, 1, 1, 1, all the x's, right? So 0, 2, 3, 4. Then I square the x's. 0 squared is 0, 2 squared is 4, 3 squared is 9, 4 squared is 16. And then these are the y values. So 0, and 2, 6, and 12. Okay, so this is our equation A x equals b. Okay, so so again, I don't have a lot of space here, so let me streamline the process further. All right, so I want to figure out A0, A1, A2. So how do I calculate this, right? So you multiply both sides on the left by A transpose. And then if I want to get x by itself, I have to take this thing in parentheses and take the inverse of that. Right, so which is exactly what we did here, right? So this thing became A transpose B. This thing was A transpose A. And then when it goes to the right side, it becomes the inverse. Right, so to calculate this thing, it's A transpose A inverse, and this thing was A transpose B. Okay, so that's the matrix calculation, right? So to save time, let's just calculate everything on the calculator. So what do I have? A 4x3 matrix. So 1 0 0 1 2 4 1 3 9 1 4 16. And then I need my matrix B, which is a 4x1, and the entries are 0 2 6 12. Okay, so I need to calculate this. I need to calculate this matrix equation. So first parentheses, A transpose A, close parentheses, inverse, open parentheses, A transpose B. Okay, so calculate it all at once. I get 0, -1, 1. Okay, so we see our model is going to be, right, so A0 is 0, so that term goes away. Then A1 is -1, so 0 minus x plus 1 times x squared, so plus x squared. So y hat is equal to minus x plus x squared. Okay, so now we have our quadratic model, and so similar to before, let's compare it to the scatter plot. So minus x plus x squared. And you can see in this case the model actually passes through all 4 points. So this is actually an exact solution to this regression problem, right? Because if you plug in x equals 0, you get -0 plus 0, which is 0. For 2, you get -2 plus 4, which is 2. For 3, you get -3 plus 9, which is 6. For -4 plus 16, which is 12, right? So this model actually passes through all of the points. Okay, so this is our quadratic model. So in this instance, the quadratic model is better than the linear model. You can actually check, go back. So here we did it using the least squares method, right? But we see that in this case, our regression equation actually passes through all of the points. And so the original system here has 0, -1, 1 as a solution. And and it could have been attained by solving ax equals b directly. Right, so for example, what do I mean by that? So let's augment the matrix A. Right, so the y values were 0, 2, 6, and 12. And if I do, if I do row reduced echelon form of my augmented matrix, you can see I get the exact same solution, 0, -1, 1. Right, so in the situation where this is actually a consistent system, the least squares method here produces the exact same answer as if you were to solve the consistent system directly. But when you have an inconsistent system, then you do want to use this method to find the regression coefficients.